This is a production of Cornell University.
Thank you very much for coming and joining in the discussion on biochar and what it is and why maybe it deserves a second look. It's of course difficult to get at all aspects of biochar. There's quite a bit to talk about, and you'll learn why and what angles are important. But I'll start early. I'll start a few hundred years ago. That Biochar Interest is actually not anything new. It seems there was, under the name of charcoal mostly, or other materials, an interest in applying char or charcoal from very early times onwards. There are some literature points here. This is in Japanese, an Encyclopedia of Agriculture. Then there was the Terra Preta discovery, quote unquote, starting with Orellana, who described fertile soils in the Amazon, where others didn't find anything. And then there were some folks in the late 1880s, 1800s to look at Terra Preta. But also in our area, Charcoal Use Elm, this is also an agricultural standard book from the mid-1800s, mentions charcoal as a soil amendment, and Justus Liebig also mentions it. Real research only happened starting in the early 1900s, and here with pine seedlings, with and without charcoal or biochar, and they described some reductions in damping off and other improvements of soil. But nothing really serious, though there were actually some products that were sold. And this is, of course, interesting for horticulture because, of course, the turf gets a lot better and the ball bounces better and whatever. And this is some kind of slang that I don't pretend to be able to reproduce here. But there were actual companies in the 20s, 30s that sold charcoal products for soil amendment. And that pretty much disappeared. And you can speculate why some of those disappeared with the advent of chemical fertilization. We're not relying so much on other strategies. But it's slowly that's shifting a little bit, and it's not only with biochar, but others amendments as well. So my story began with these soils. As was mentioned in the introduction, these are the Terra Preta soils in the Amazon. And if you can see the color is quite different of these adjacent soils. They might be just tens of meters away from each other. And this being the Terra Preta soil, very, very dark, far down, in some instances up to 2 or 3 meters down, very black soils. Whereas those are the adjacent soils. And of course, they're much more fertile, these black earths. It's the same guy, same height, same day. So you see that the corn here is a lot shorter. And this was a study that was controlling for the age of the secondary vegetation that was cleared before the trial started. And the darkness here is from char compounds. And that was proven in the late 90s. Why they are so dark is from charcoal, though a lot of other things happened with Terra Preta, and that's why it's not a perfect study object for the effects of char, because there are a lot of other things that happened. These are anthropogenic soils that received a lot of other things as well. But I studied in the time when these experiments were done in the Amazon, and got interested in looking at this a little bit further. But there's also a Cornell story that reaches back over 100 years with this guy. All of you know, of course. It's Charles Hart. You might not know it. He's happened to be a geology professor here. He was the first chair of the geology department in the 1870s. And he wrote a book about the geology and physical geography of Brazil, and for the first time that we think it has been scientifically described, the Terra Preta, more so by his graduate student, the Cornell grad Herbert Smith, in his book Brazil, the Amazons and the Coast. So there's a Cornell, and just for a fun factor, this is an early slide, an early PowerPoint from Charles Hart. He painted it himself. And this is a canvas that's now in the Kroch Library. That's about the size of this whole front panel here. So this is what 100 years ago the professors would roll up and show you instead of PowerPoints. It was a lot more work. They got a lot more exercise out of it probably. So there are about, I think, 5 or 6 of these huge canvases in the Kroch library. First, when I tried to find them and take photos of them, they couldn't find them again because they were so big they had to store them somewhere underneath some racks and couldn't find them. So Biochar Interest has emerged. The term itself only came about in 2006 through 2 of our publications, and here in Google Trends, if you want to believe these, gained some prominence in the public domain. So it was spoken about if you compare it with the hits that bioenergy got in comparison to biochar. So there was some great interest. Luckily, it has died down a little bit, which afforded us the opportunity to do science and not do public relations. And science we did. We is the capital. We all, you, some of you, we as the scientific community. If you look at the number of publications since 2002, dabbling around just a handful each year, mostly under the name of charcoal, but then in relation to soil application, and shot up the last couple of years tremendously. And now the red dots show the proportion of biochar research and charcoal research as a fraction of compost. So we're sort of at half or a little bit above half the publication volume that is happening in compost. So that's quite a bit achieved over the last 2 or 3 years, considering that most researchers only started about in this year to get funds or allocate some of their existing funds to biochar research. And we'll probably see a tremendous increase because most universities in the US are now having at least one program in biochar research. And these are some reports. This is our book that we wrote published in 2008. So you can see a lot of the information that is contained in these publications is probably now redundant because most of the peer-reviewed publications became available only afterwards. But biochar is actually not really a material. That sounds a bit odd, but it's actually a system of how we deal with organic matter and nutrients in an agricultural landscape. It's more than just a material that I buy in a bag and put in the soil, because you might have an interest in biochar because it's actually a waste management strategy, and that's maybe one of the older ones. There are pyrolysis units have been built for decades that are waste management tools to get rid of certain wastes and densify them and then landfill them or do something with it. So it might be a waste management tool. It might afford you the possibility of mitigating climate change, but as I show you, there's much more to that than just producing biochar. You can actually accelerate and emit carbon dioxide, net carbon dioxide and greenhouse gases by producing biochar. So it's a systems question. You might produce energy at the same time as you produce biochar, because the off gases that are coming off during pyrolysis can be used as an energy carrier, and it might lead to soil improvement. And the question is always, where are you? Do you need to harness all of these benefits to be sustainable and have social and financial benefits? Do you need to be in here, or can you be out here in any of those to make it work? We'll talk a bit more about, because of the audience and your likely interests, about the biochar product, something that we might put to soil and have expectations of soil improvement. We probably are likely also interested in stability of that material because that's one of the charms of biochar. If it improves the soil, it might do so for a very long period of time. So that might be interesting. And just to set the stage for what biochar is, it's really a fundamental change in chemistry, making biochar or char out of biomass. The color changes. Now these hazelnut shells become black. You fundamentally change the chemical makeup into something that's much more aromatic, though very heterogeneous compounds. There might be not perfect structures, highly interlinked, And as the temperature increases, especially beyond 600 degrees, you see then more orders coming up, turbostratic, so-called turbostratic carbon increasing, and again changing the structure of the carbon at very high temperatures, which might not be relevant for biochar as a soil amendment. You might find a highly ordered structure, but that happens only in the thousands of Celsius. Whereas the chemistry really fundamentally changes, completely changes. The morphology, as you can see, the hazelnut shells still look like hazelnut shells. They're black. A banana would still look like a banana. There are people who do that. They try that out. It still looks like a banana. And microscopically, it actually also, to a certain extent, the morphology looks like the original material. So you can still see the xylems, phloems. You see all the plant structures. So what you put in, you get out. The dimensions might be a little bit different. The chemistry of the minerals might change, and definitely the chemistry of the carbon changes. And one of the profound changes are the stoichiometry between oxygen and carbon, and oxygen and carbon and hydrogen. You devolatilize and condense the carbon structures with increasing temperature. You decrease both the HC and the OC ratios towards something that's carbon rich and oxygen and hydrogen poor. And you see that more or less everything is on a straight line here with greater temperature increase, and there's a good relationship apart from these buggers up here that look very, very different. And these are the oddballs, biochar made from paper sludge, biochar made from poultry, so high mineral feedstocks and low lignous feedstocks that are falling out. So there is still, apart from the fact that several are lining up very nicely and we can describe them very well, there is still quite a variety, and some of them might fall out. So we definitely need to understand better what the formation conditions of these kind of biochars is, and whether they are of any use as a soil amendment, a soil conditioner. We have much more experience with woody materials. The volatile compound, which is a measure, a laboratory measure of the thermal stability, which has often been equated to also recalcitrance against microbial decomposition, correlates somewhat with the HC and OC ratios and works quite well. But again, here we see that some of the others, these odd ones, paper, poultry, are falling out of these equations. But this affords us the possibility to analytically distinguish those, whereas with the OC and HC ratios that was not really possible. They overlapped. With this technique, we can actually separate analytically materials that have high so-called volatile contents from those that have lower volatile contents, and then work with stoichiometry to understand, for instance, stability a bit better. So we understand that there's a huge variation in properties with these comparatively simple analytical tools. And here you see it's in a different way. Ash content alone, you see we have some materials here from paper mill, poultry, for instance, that have 50% and more ash content, to some woody materials that have barely any ash content. The fixed carbon or volatiles, which is the subtraction of one of the other, they add up to 100%. You'll see that we might have no fixed carbon and only volatile carbon in some, whereas we have more than 60% in others. And the temperature plays a big role. Increasing pyrolysis temperature from 300 to 600 degrees, you can see, typically increases the so-called fixed carbon content and decreases the volatile carbon content. So both feedstock and temperature of formation play a big role in what the biochar looks like, and feedstock plays a huge role for the ash content. So we have a huge variety of different materials. If we map this out on such a triangle that we are familiar with very often from soil texture analysis, and map out volatiles, ash, and fixed carbon content, and the arrows always point from the lowest formation temperature to the highest formation temperature, we'll see that we increase the fixed carbon content and decrease the volatile carbon content with higher temperature. But that trajectory actually changes with high ash material. So something's happening. It's not only just more ash in some of the biochars, but the ash content has a profound effect on the organochemical composition of the entire biochar. So it's not just more nutrients or ash or silica in some biochars. So likely also the material itself, the carbon material itself, is fundamentally different when you have high ash content. And that's nicely shown in here. So we have a lot of variety between different biochars, but we unfortunately also have a lot of variation within the biochar. This might be a mock-up of a biochar particle. I'll imagine that to be a few micrometer large. And then you have probably more ordered structures, more folded structures. You might have some organic matter adsorbed to it, some microorganisms here. So there's a huge amount of variation also within each biochar, and that causes challenges for us for characterization, but also it causes challenges for us for understanding what actually how we actually might explain some of the effects that we see on a microcosm or a field level. When you char, you transform the carbon, but you also do something with the nutrients. The maybe most interesting one is, of course, nitrogen. We manage organic matter very often with the intent of managing nitrogen. And very often we do that because we like to add some organic nitrogen that hopefully will be available for a plant to take up and improve crop yields. That's, of course, very different for char. When we do a thermochemical conversion, a lot of the nitrogen might volatilize because we're doing a thermochemical conversion during that thermochemical conversion. But funny enough, that is very different for different organic materials. A pine that is low in nitrogen, actually the nitrogen contents increase. The yield ratio increases. So we're getting more nitrogen in the biochar in relation to carbon, whereas with a high nitrogen containing poultry litter, for instance, we're getting a net loss compared in relation to carbon. So there are interesting things happening, and we're just now with one PhD student looking at what these nitrogen compounds look like and how they might be available. And our expectations is, of course, that the nitrogen content is not very well available, and that we largely lock up nitrogen in highly recalcitrant compounds, which poses a challenge for the overall nitrogen balance of an agricultural ecosystem. Counterbalance, something that I won't be getting into much today, is that we very often find increased nitrogen use efficiency. So the nitrogen that we actually add to the soil is taken up to a greater extent by crops in the presence of biochar through retention mechanisms. A big portion of the attraction, as I mentioned earlier, is the stability, and I'll only go into this quickly, and I'll have a whole seminar just on stability. But what we can walk away with is that typically biochar is an order or more stable than the uncharred precursor material. There might be some exceptions. Paper sludge might be one, but typically the uncharred is much more labile against microbial decay. But we have some issues in characterizing that, and I showed you some results from proximate analysis, OC-HC ratios. There are some fancier spectroscopic techniques that we employ to instill some confidence, because that is, of course, a big discussion item. How sure are we, and how can we demonstrate it for a given material, how stable that is. How this leads to climate change mitigation is, you need to think about it. It's as I said, it's not just the biochar itself. It's a systems management. In a normal system without charring or fires, we would have some fixation of CO2 by photosynthesis, some auto respiration, Organic material through root turnover or leaf litter fall would get into the soil, and then in an equilibrium on an annual cycle probably be mineralized to the same degree as it is getting into the soil. And that depends a bit on what kind of system we have. But so if we conceive a biochar system, we would look at using the material that would otherwise in the same time frame mineralize and pyrolyze it in something that's much more stable, add it to the soil. Half of it we would hopefully in many systems use as bioenergy and offset fossil fuels or other wood or other biomass that would otherwise be used, and add it to the soil, in which it would remain for a much longer period of time, which would mean a decrease in emissions and therefore a net carbon withdrawal from the atmosphere. So important is to realize that still the CO2 withdrawal or the CO2 capture from the atmosphere is delivered by the growing plant. All we can hope to do is decrease the return of CO2 to the atmosphere by deviating some of the fast cycling biological carbon cycle in a much slower cycling biochar sort of geological carbon cycle. And we do have choices. If we are starting with 100% of our initial carbon stock and just let the tree grow, for instance, or the vegetation grow, we might get still a bigger tree over time. And anything we do, if the baseline scenario was growing the tree, we would of course emit carbon. So we have to use opportunities where under a baseline scenario, the carbon would be emitted. So we're looking then at, for instance, a decay of fresh biomass, maybe woody biomass, or this orangey line, fresh biomass herbaceous or crop residues, field crops or horticultural crops that would decompose very quickly over time. If we char, we immediately volatilize about half of the carbon, but the remaining carbon is in most cases much more stable than the biomass carbon. And although we have had here 100% and here only 50% at time zero, we would probably after some time, and that depends very much on the lability of our original material, have more carbon in soil than under the baseline scenario. But you see that there are big differences whether we have this baseline scenario, this one, or that one, and we need to recognize that. Even if we have identified an opportunity to have a net carbon sequestration, we're still probably dealing with different turnover times or mean residence times. And depending on the mean residence time, we will have eventually a scenario where we will have more net mineralization than we can net sequester. And that's illustrated here just theoretically with made-up data, just model data, but which illustrates that just fine. Here the net sequestration effect of biochar scenarios where the biochar has a mean residence time of 50 years, 100 years, 200, 500, 1,000, and 10,000 years. And you'll see that as a fraction of what we might apply as an annual maximum, we would see that we would, under a scenario of 500 years mean residence time, we would reach peak biochar somewhere around 50, 60, 70 years, and then have a slightly declining net sequestration. Only if we have really high mean residence times, and this is considered a very high one, would we have this for very long, hundreds of years. So we're looking probably at a strategy from simply the mean residence times as something that helps us transition out of a fossil fuel future into something else, but it's not a perpetual strategy for the next hundreds of years. Another layer of complexity is that it's of course not even only the biomass that we use and the stability of the biochar itself, but there are a lot of other points in a biochar system that might generate or reduce climate gas emissions. and that might be with transportation, might have to do with transportation, avoided emissions from biomass decay, the energy that you produce, transport, tillage, soil carbon changes, and so on and so forth. So we tried to put this all into a big model and have published a few that just looked at the life cycle of individual projects, but also some that looked at the global scale. And this is the global scale analysis that was published a couple of years ago. And what we came away with as a maximum sustainable technical potential. That's really, if you did that all over the place, as much as we thought with quite conservative yet quite ambitious assumptions. So discounting if you had to have soil protection, discounting biomass availability for and use for other purposes, we came away with somewhere in the 1 gigaton annual emission reductions, which is not insignificant, but it will not. It's about an order of magnitude, or not quite an order of magnitude, of the total emissions with fossil fuel. So on its own, it will not save the day, but it's as a package with another 20 or so sequestration on emission reduction strategies, it might play in there. Something to point out also is the dashed lines are comparative scenarios if we use biomass for combustion and energy generation. You'll see they're always below the equivalent straight line or filled line. And the reason for that is that the difference is really the soil effects of the biochar. If there were no soil effects of biochar, either reduced gas emissions, improved growth, or any of that, they would overlay each other. So we have to have a soil effect. But at the end of the day, and this is a survey that we did for projects that are conducted in developing countries, and it's already 1.5 years old. We asked for this World Bank report that's still not out, existing projects that were selected from 150 projects down to, at the end it was somewhere around 50 projects. How important carbon sequestration or carbon credits and mitigation of climate change was to their project. And there was only a quarter of the project that said it's really important. The other said, not important at all, or yeah, we'll take it, but we don't count on it. So, and I think that's the sentiment throughout a lot of different projects that have to do with mitigation of climate change. That other ecosystem services and agronomic improvements are topping climate mitigation incentives, and because carbon credits are not really anything that anybody counts on at the moment. So why biochar is added to soil in the US and the northeast of the US is mainly because farmers, landscapers are interested in their improvements of growth or other factors. There are now companies that look at green roofs. There are companies who look at turf. There are companies who look at greenhouse operations and a few in horticultural crops and field crops. Here, just a way of thinking through some of the issues with a growth experiment that we did here in the greenhouse with soils from the Musgrave experimental farm, where we looked at different temperatures of formation, different feedstocks, and gave that to a maize crop. And here you see biochar added at different rates, 0.2, 0.5, 2, and 7% by weight, which equates somewhat to about 2 tons per hectare, 5, 20, and 70. And the biomass production of the corn in comparison to the dashed line, which is the control. And you can see that there's a widespread. This is for 300 degrees Celsius for these kind of different feedstocks, and we did more of those different other feedstocks, woody and crop residues. But you see from a significant increase, from a 40-50% increase to almost a complete die-off with everything. So you can do almost anything. You can kill plants and you can improve crop growth quite dramatically. So obviously, and all of that we would maybe call biochar. So obviously we need to understand a little bit why one kills the plant and the other one does just great. And is there really anything that we know goes beyond very simple explanations that we might achieve with a lot of other management interventions as well? If you look at it with an analysis of variance and just do some statistics, now some feedstocks come out on top, poultry manure, and likely that has a lot of nutrients in it. Food waste, so whatever the Cornell students and faculty, I guess, don't eat is doing really poorly. So what we don't eat, we shan't give to plants, is the rule here, or something like that. Temperature has a significant effect. 500 degrees Celsius was the best, but no, without dwelling on this too much, all the interactions.
What were those numbers? Were those like dry weights of crops? Or
Yeah, that's plant growth again. Okay. Sorry, that's a gram of plants in the pot. Yeah, good question, thanks. But before we dwell too much on it, all the interactions are also significant. You know? So you can have something. So the averages over all feedstocks are almost meaningless because you might have a different feedstock might have a very different temperature of that the plant growth was the greatest. So all the interactions were significant. So it's a highly complex response that defies simple regressions and simple analysis of variance. And then we tried a few other conversion processes that the blue ones are all the ones that I showed you with the feedstocks. But we tried also from collaborators updraft, fast pyrolysis, flash pyrolysis, gasification, torrefaction, and threw in an activated carbon from Japanese colleagues that they put in hundreds of golf courses in Japan. So they're going every few years and put that stuff in golf courses. And you'll see that this didn't do all that well compared to the control, which is the yellow one. This is, again, total biomass in that pot of maize. And you can see that there's no clear picture that all the gasifications are doing well and all the slow pyrolysis are doing bad, although it orders somewhat with feedstock. All the poultries are on the left side and all the foods are on the right side. So there's somewhat a pattern there. The problem with the food was mainly a problem of sodium. We found that a lot of the food waste had a lot of sodium. No, we put too much salt on our food. We know that. We shouldn't do it, and we definitely shouldn't do it if we want to put it in the soil. But of course, also that might be managed either because you might put less of it on. 0.2% was just fine. It didn't decrease anything. You might not put 70 tons on, which nobody would dream of putting on anyways. Or the sodium might leach out very quickly with the first rain event, or might be post-treated in some ways. But it's definitely something to consider. We tried to correlate that with different parameters. We thought maybe the specific soil surface area would have anything to do with the ability of the chars to improve. Some growth parameter didn't really come out. pH, no, only mildly. None of these parameters that I showed you earlier. Carbon, nitrogen, also not really. If anything, then it was negative. So there were some weak positive correlations with nutrient contents, and then the negative correlation with sodium. So we didn't really find a simple reason why some of the plants grew well and others didn't. Sort of reflecting the mix of different responses that we saw to input variables of temperature and feedstock. A good example why this is not the end of the story is always pH, which is a very simple way of showing the potential of manipulating and maybe designing different biochars for different options or different soil constraints. And you see here the ash content versus the pH measured in potassium chloride. for all our chars, and we group them here together. Oops, that we don't need. And you'll see that there's quite a big spread here. We can produce biochars with a pH of close to 4. We actually have sometimes produced it at 4 or below, and close to 12. That's a huge spread, and you all know soils that we don't want them have here or here. We want to have them somewhere in the middle here. So there are opportunities, and as you see here, again, the arrows point from the lowest temperature, pyrolysis temperature of the same feedstock to the highest. We can produce biochars from the same feedstock that have either a pH of 4 or 5 or 7 or 8. So even if we are locked into a certain feedstock, we might have the possibility to change our biochar product quite significantly. And that's not a bad way of manipulating our organic matter amendments. That's very different to compost, for instance. We probably get one type of compost out when we make compost, and it has a certain pH. It might be of poor quality or of higher quality, but the ability to change when we have a certain type of feedstock input to change the output is very difficult, and with managing composts is also not that easy. Whereas conceivably, and doesn't work always that way. Conceivably, we can dial in a certain temperature quite precisely and produce a biochar of a very specific type. Agronomic effects might differ not only with the biochar type, but also with the soil. It's very clear, although some users and those not so familiar with soil science and agronomy tend to forget that. I won't insult you with these negligence, but it's very clear that on a feral soil, if you put something on a biochar with a pH of 9 or 8, you get a significant positive response simply for pH effect, and there might be other things happening, but I would not claim that this is probably a lot of it is a pH effect. Whereas on a calcareous soil, the wheat will probably not respond or even go down, and the same with soybean. So we really need to start with the soil constraints. If we identify a soil constraint and we think that biochar can do something about it, then we need to produce the biochar that actually can do it. If we had put a biochar with a pH of 3 on this would also maybe not have grown any better. So we need to really design biochars to the soil constraints that we identify. That's the easy one, the pH and the pH of the soil and how it might address acidity or alkalinity. A notch up more interesting and complex are the effects of biochar on nutrient leaching. Here's an experiment from a molly-soil from Iowa where biochar was added. These are the different additions with high additions of 20 tons, 10, 5, 0, either with manure additions, which is the filled symbols, or without manure additions. And you can see when you add manure, you have a lot of phosphorus leaching, but the more biochar you add, this phosphorus leaching goes dramatically down. So it seems that there might be mechanisms, and we've shown that there's a higher cation exchange capacity on chars per unit surface area, per unit mass, than on any other organic matter that we have looked at. So there are opportunities to retain cations. Obviously, phosphate is not a cation, but an anion. So there are other things going on. Could be calcium phosphate formation, could be calcium bridging or hydrogen bridging, could be something else. This is not yet known, and we're working on that to find out a bit more. We can have exactly the opposite, and this is Marty and Mark's data from turf here at Cornell. Mark's thesis looking at biochar that was made from turf charred and a sand control and peat, so the gold standard, and you can see with peat compared to the sand control, the leaching went down, but with biochar it went up quite a bit. So the opposite of what we showed earlier. Well, this biochar, it turns out, has a huge amount of phosphorus in it already. So it actually didn't retain any phosphorus, it contributed phosphorus. The grass grew a lot greener and better. So that went very well, and there were some interesting effects on disease, but it was definitely not useful to reduce phosphorus leaching. So again, we need to also, for that, we need to know our biochar, I guess. There are fancier things going on. Interesting, the disease severity. These are colleagues from Israel. They have now 2 or 3 papers on this, different diseases, and they consistently find reduction of disease. And they looked at different diseases in different plants, and I don't quite remember whether this is just a placeholder, but they found with 0, 3, and 5% a significant reduction in disease severity. And they try to link that to a change in microbial associations in the rhizosphere that they think, judging from other papers, might have an effect on systemic resistance of the plant. So those are a few interesting leads worth following up on. With Eric Nelson together, we've done some preliminary tries with Pythium here in plant pathology, and he also he finds with the soil-borne disease, the Pythium, that we have lower disease severity with biochars, and we are currently clueless of why that is, and we of course don't trust our results until we know why we find that. In another attack, we are trying to understand whether we can produce inoculant carriers based on earlier results. Now, this is from the 80s, but there are results from the 30s and 40s, where very often inoculant carriers were used that were based on charcoal. Peat is, of course, the gold standard now, especially Australian peat, as an inoculant carrier for rhizobium. And you can see that the biochar was as good as the gold standard peat over this 120 days. And we have a project that looks at that. These are some early results from that, some MPN numbers from biochars made from pine at 450 degrees, from oak at 700, and oak at 450, compared to the peat. So the peat did very well, so we didn't screw up anything. Well, initially we did, but this worked out very well. So these are acceptable values, these are good values. But you see, we can also, again, we can choose a biochar that really backfired, and these are unacceptable numbers. This is a log scale, so these are really low numbers for microbial rhizobial survival. But these are very good numbers. And of course, there might be opportunities because the biochar that we might produce is instantly sterile at 450 degrees, and not a lot of microorganisms that survive that. Whereas the peat, you have to autoclave, and that might be a challenge in some countries, let alone to get Australian peat. In some locations might be a challenge, and it's a non-renewable resource that is only to increase in price. So there are some opportunities for such products, which of course are very small and specialized markets. Because it's also so different, the biochars, we really need to have a framework for it. We founded the International Biochar Initiative a while back, 5-6 years or so, and went through a guidelines exercise in the past couple of years, where we tried to define what biochar is, because there are people who use old tires and pyrolyze them and call that biochar, and all sorts of things. And of course, there's no definition. Nobody has defined the term officially. We tried, but nobody listens if just there are individual scientists writing papers who looks at them. So we tried to come up with standards and want to, in the future, develop also sustainability standards for systems. So this is where we are. Reviewed criteria, had in-depth reviews. There are webinars that were held in 2 waves There was public and commenting period, so very much modeled after ISO and other international standards, and trying now this year to provide a first version of it. And there are different levels of stringency of characterizations that we propose, and I don't want to go into detail. The iffy one at category A is the amount of carbon. How much carbon is there in biochar, and that would exclude some. And what's the HC ratio? And that will exclude others. And that's become a big contentious discussion because some producers and also researchers, of course, have different opinions about that. So it was very interesting to see how we can have different a consensus, an international consensus on that. And then there are obvious PAHs and furans, dioxins levels, but very often these are not even published for composts. So it's very hard to come up with some of these levels. Heavy metals, again, there are some compost guidelines, but also not as straightforward as you would think they are. Here you see that temperature affects the HC ratio of the biochars with increasing temperature, lower HC ratio, as we've seen earlier. And 0.7, you'll see that will include some of the black dots here. Where should that limit be? At the moment, it's 0.7, so anything above would not qualify as a biochar according to these standards. And Australia is using a different approach. They're using a recovery of 20%, so they're looking more at the system, not as a biochar property, not as a material property, but more a systems recovery of carbon throughout the pyrolysis process. Very different approach. So just briefly, a few pictures rather of biochar production. So this is of course charcoal production from way back when. This is not a good way of doing it, right? This is how it happened very, of course, throughout upstate New York in the 1800s. Most of those were abandoned in the 1880s when we switched completely to anthracite for pig iron production. But that's why we have decreased our forests here so dramatically in the 1800s because of this process. This is, of course, all energy. This is lost energy. We get only 20 to 30% charcoal out of 100% biomass. The rest is smoke, but it's all energy that we can capture. This is a unit from 3R in Hungary that are coming out of the waste management area. So they are producing biochar for soil amendment. They are certified now. They can sell that in the EU. They have had trials in 3 countries in the EU, so they have a marketable product right now. They don't capture energy. This is a small pilot project in Australia that actually produces electricity while making biochar. This is a first project, although I think the 3rd generation of an NGO called Pro Natura, founded in Brazil originally, here in Senegal, with a unit that produces biochar made from invasive weeds along the Senegal River. And this is biochar production in British Columbia from a lot of the pine beetle kill. So this is a mobile unit, comes on a semi in the back, and can produce biochar wherever these kills are as a baseline scenario in comparison to just flaring them up, because that's what they're doing currently. So those are some technology solutions that we might look at. We are looking at building units that are smaller than what you've just seen. Well, it might be about this size, a bit bigger actually than this size. We're currently working with the engineers in a couple projects to model the flows of gases and the combustion through such a system where materials fed in and then transported through. Full gas recycling for the 2nd generation. The 1st generation will be much simpler, and this is what such a unit will look like. And some of you might have seen that in Leland Hall here up the road. We were able, with lots of support and goodwill, to renovate a portion of the Leland facility with all kinds of safety things. You can imagine New York State is about the worst place. Maybe California is even worse. But in terms of regulations to comply with all kinds of things, they put sprinklers in that are probably would be fine for a nuclear disaster. It's amazing what we had to put in this facility for this little thing. But there's quite a bit to do, and building such a facility here, being able to produce maybe hundreds of kilos of biochar per day, tons in a week, and staging field trials is an ability where we can understand a bit better what the crop and plant effects are beyond the simple ones, pH, cation retention, and the simple nutrient additions. I think now it's time to do some adaptive science. There are initiatives also here in the there's Finger Lakes biochar groups, there are Northeast biochar groups, they're all cropping up, and they're all doing, starting to produce biochar, and they're biochar, I didn't manage to do that, but you can buy biochar in a package on Amazon.com, and of course we don't know what's in there, and nobody will tell us either. But we need to look at what that does for different soils, and then all the market analysis will be very different whether we have an inoculant carrier material or whether we put something in large amounts to row crops. So that will be very different, and I'm sure it will. The opportunities will vary and not be universal by any means. Thank you very much for your attention. I'm happy to take any questions that you might have time for. Thank you.
And I'm going to turn the volume up on Geneva so we can hear them again.
Here.
Can you tell us a bit about how the Terra Preta was originally formed, whatever, millennia ago? What was the process that led to those soils?
Yeah. So that's a big fight that luckily as a soil scientist I don't have to partake, but it's not known. There are C14 ages that go up to 9,000 years. So some of them are pretty old. Some of them are just 500 plus. And there's really, I've not seen any C14 dates that are more recent than 500 years ago, simply for the fact because we were very efficient in
when Columbus got here.
Right, yeah, this was all. We brought pigs and we brought influenza, and that was that. So there are some reports of indigenous populations that are still producing Terra Preta and biochar, but it's a bit contentious. Some say it's really a byproduct of habitation, accidental from how they lived and what they swept. Some say this can't be true, and we've calculated it also through you cannot have from fire and burning the black carbon amounts that we today find.
Right.
Even
slash and burn.
Slash and burn. If you do the numbers, what we find today cannot be created by slash and burn or fires or kitchen fires. It's impossible. There needs to be some purposeful addition. But what that was and whether they recognized that this was something they should do remains a mystery. For us, luckily, we know when they were added. We can measure it now. It doesn't matter. But the archaeologists are in a much tougher spot because they need to explain it.
And what percentage of the Amazon basin would be Terra Preta?
Yeah, that's a big question also, and the numbers in newspaper articles go from 0.00 something to 10%, and anything in between, not known. So circumstantial evidence is that you can get out of the car almost anywhere and ask somebody about Terra Preta, and they within 15, 20 minutes they guide you to somewhere where there is one. But then sometimes they're only half a hectare, quarter of a hectare. The big ones are underlying the big cities of Manaus, Santarém, and Belém. They are several hundred hectares large. So if you get the chance on drilling through some of the floorboards and the big downtown houses, then you find Terra Preta underneath. But we don't know. My best guess is that it's less than 1%. So it's not half. I don't think it's 10%. But that's just my guess. Yeah.
What's the gross energy input
Well, the process is exothermic, so you're actually gaining energy, but what you're losing is, of course, mass. It's similar to a fire in the fireplace at home. You need activation energy, which is the match or a lighter, but once it's starting, it has enough energy to perpetuate the process.
And so what is that initial input that you have to contribute?
If you let the machine run 24/7, you know, it's nothing. It's a fraction of a percent. It's absolutely nothing. If you ramp it up and down every day, then I don't know what it would be, but you would never do that in a commercial facility. So once you provide the activation energy and you have gas recycling, then it just is driven by your own off gases. But if you're only producing biochar, you're wasting 70% of the energy, 50% of the carbon, and most of the hydrogen and oxygen. Why this makes, from a systems perspective, why this makes sense to think about it is because while you're actually, for us as agricultural-minded people, is that you're retaining half of the carbon, roughly, and put it back in the soil, while volatilizing 90% of the hydrogen and oxygen. That you don't have maybe a lot of use in the soil anyways, as water and CO2. So it makes sense to look at this from a life cycle perspective, because you can get 70%, 80% of the energy out of the biomass while retaining half of the carbon as a soil amendment. So that's a starting point why this looks like, from a life cycle perspective, looks like a good idea. Yeah.
Do you have any estimates of how much soil or what fraction of the soil, say in the U.S., might be available for practical biochar amendment?
Yeah, none whatsoever. But very good question. That would be a good title for a project.
Oh, okay.
Excellent title for a project. Yeah, I have no idea whatsoever. There are some researchers in Connecticut. They are looking at asparagus, for instance, onion. That looks very promising. They find very good results. In the Midwest, on the mollisols, we would not expect any positive results, but they're looking at different withdrawal regimes. They're comparing with and without biochar additions at 80% residue removal for bioenergy, 50%, and they think that they would be able to maintain carbon levels in soil with higher removal because of the biochar. We've done we're in our 6th year at Musgrave here up the road in Aurora, and added biochar. We've seen no positive effect on yield, and we didn't really expect. We see a slight improvement in nitrogen retention and nitrogen and reduction of nitrogen losses by leaching and denitrification, but no improvement in crop yields with corn. So we have a little hatch grant where we want to try out maybe 30 different soils from upstate New York and see which kind of biochar works on which kind of soil. So that's a first step towards that. And we have a couple of different projects in Africa where we do that as well, with the Mike Knight Foundation, so for instance, to try out that for Ethiopia and look at a gradient of different soils and try out what soil constraints there might be and what opportunities there are for biochar to address those. Yeah.
Johannes, will you ask Geneva if they have any questions?
Geneva, do you have any questions?
Yes. Yeah, I'm wondering about, on the other end of it, for New York, what do you see as potential feedstocks for biochar production? What kind of organic materials do we have available in sufficient quantities to make this interesting?
That's a good question. We calculated a little bit through because it's attractive to look at the waste biomass first, and we looked at yard wastes, and that looked fairly positive. It would be interesting to start something here in Tompkins County that are not very efficiently using their collected yard wastes for composting. There are some feedstocks. We don't have as many feedstocks in upstate New York as for instance, some of the problematic feedstocks that we're working with in New Jersey is poultry manure, where we see some opportunities in earning also nutrient credits. There's one project in Pennsylvania, and Pennsylvania has a new nutrient crediting program, similar to a carbon credit program, where they get money for getting phosphorus out of watersheds. And densification through pyrolysis is a good way to do that and still have a marketable product. So they are hoping to earn nutrient credits by producing biochar and have still a marketable product. Yeah. So it's a work in progress. There's a lot of interest from farmers and landscapers, but comprehensive analysis hasn't been done. Good question, though. Yeah.
I just wondered if there's any work done on the physical effect of biochar on the physical characteristics of the soil in terms of the.
Yeah, that would be
what's the particle size? If there's any standardization of that.
Yeah, there is not. You can modify the particle size. It depends a lot on the starting material. If you put big chunks in, big chunks come out. For many feedstocks, for some of the grasses, you get fine powder no matter what you do. For fast pyrolysis, you get fine powder. For slow pyrolysis, you get slightly coarser powder. So there's all that consideration. Very few projects on as simple things as moisture retention curves, structural stability, aggregate stability, penetration. Very, very few data. There's one project funded by the NSF at Rice University that looks at moisture retention curves. We've done a little bit, but not enough to really say anything about it. There are about maybe 5 papers out now, and it's not it's not conclusive what they would be saying. But we know that any organic matter added to soil improves typically field capacity and moisture retention that's usable for.
This has been a production of Cornell University, on the web at cornell.edu.